So as you can see from your handout, we're actually kind of going back to those fundamental identities for these trig functions. And we're going to try and work with those to try and, of course, evaluate our trigonometric functions so that will look familiar to what we did before. Simplify those expressions. We're talking about developing additional trigonometric functions and then, of course, solving equations. So all of these fundamental identities that you see here, we've talked about these in chapter 1. So you've got your reciprocal identities, quotient identities for your tangent and cotangent, Pythagorean, we've talked about those. We talked about cofunction identities, and then of course, remembering that cosine and secant are the only two even functions. Sine, cosecant, tangent, and cotangent are all odd functions. So again, they're saying it may not be a bad idea to remember these fundamental identities. The one thing you have to be careful about in these identities is how they are defining that angle u. So it can be an angle, but at the same time, they can also use it as a real number, or they can think of it as a variable. So it's going to depend on what purpose are we using that u for, and then how would we go about solving for it. Now with those Pythagorean identities that you saw right here, so remember, if you're trying to use the cosine value to find sine, you would need to move the cosine to the other side, get sine by itself. So you can actually think of them as the square root property being applied to try and find the missing function. So that's kind of what they're talking about here, is maybe sometimes we may have to do the radical form, and then the positive or negative value will depend on what quadrant your angle u is falling into, right? So again, that would say, do we need our angle to be a positive number or a negative number? All right, so let's take a look at how we can use these fundamental identities. We've got a basic example here. They're asking us to evaluate the function based on the information we have. They're telling us secant of u is equal to -3/2, and tangent of u is going to be a positive value. And based on that, they want us to come up with the six trig functions here. So in what order you find the functions will depend on you. As you can see, since we're talking about a secant function here, secant of u equals -3/2. If you take its reciprocal, you get the cosine function. So that's where we started out with. Cosine of u will then, of course, come out to be the reciprocal of that fraction, and you end up with -2/3 as the cosine. Once we have the cosine function, we can go find the sine function. So you'll see we're using the Pythagorean identity here. So we're substituting for cosine of u with -2/3, take that to the second power, and then subtract that answer from 1. And that's giving you sine squared as 5/9, right? Now this is still square, so you will need to take a square root on that function and come up with what the sine of u is going to be. Now this is where the sines is going to play an important part. So we know secant is -3/2, which means our cosine also came out to be -2/3, but tangent function is positive. So if tangent is positive, cosine is negative, what does your sine need to be? Sine also needs to be negative, so that's why you've got that -√5/3, because two negatives make a positive, right? If cosine is negative, that means sine also has to be negative. So that's why you end up with square root of +5/3 and then slap a negative on the whole fraction. So you've got your sine and cosine functions now. Take a ratio of those two values to get your tangent function. Tangent comes out to be √5/2. Once you have the sine function, take its reciprocal, and you're going to end up getting the cosecant. So that's -3/5. Rationalize the denominator, so you get -3/5/5. They actually gave us the secant of u function, so we know that's -3/2. So technically, you are not finding 6, but 5 functions, I guess. And then take the reciprocal of the tangent function to find your cotangent function, and you've got cotangent of u equals 2√5/5. Again, we're basically rationalizing that denominator. So using that same concept, like I said, this is something we have already done previously, but we're kind of bringing those concepts back again. So they're telling us tangent of x is 1 over 3. Cosine of x is a negative value. So what will that come out to be for our other functions based on that? So let's take a look at this example here. Okay, so we've got tangent of x equals 1/3, and they are telling us cosine of x is negative. So if cosine is negative, tangent is positive, what will sine need to be? Sine will also need to be negative, right? Because again, two negatives make a positive. So, I'm actually going to write that down so we'll remember that sine also needs to be negative. Okay, so based on the tangent function, what's the first angle do you think we can find here out of those? Sorry, not the angle. Out of the 6 trig functions, what can we find next? Cosine and sine? Can we do that based on this? Not just on the fundamental identities, right? Can you find secant? Cotangent, that would be my first thought. Yeah, it's cotangent, because what would cotangent be? There you go. Yeah, it's the reciprocal of the tangent function. So over 1, which technically is just 3, right? All right, so we've got cotangent. Alrighty. So now which ones do you want to find next? You were saying, somebody said secant. Based on which identity? Yeah, very good. Let me pull that up. So if you know the tangent function, you can use the 1 plus tangent squared of u equals secant squared of u. So we can use that to find our secant. All right, so let's do that next. So we've got 1 plus tangent squared of u equals secant squared of u. Tangent is 1/3. Square that. And you know what? Since we're using x as our angle, let's change that to x. Okay, so if you go through the math, what do you come up with? Go ahead. 10 over 9, okay, yeah, because when you do 1/3 squared, that's going to become 1/9. And then basically, this guy is going to convert into 9 over 9. So 9 plus 1 will give you 10/9. This is still secant squared, right? So how do we find just the secant? Yeah, very good. Take a square root on both sides. So that would be plus or minus square root of 10 over 9 to get our secant of x. And cleaning that up, what do you get? Can we do square root of 10? No, so leave that guy as it is. Square root of 9? Very good. Now the question is your secant function going to be positive or negative? And how do you know? Okay, and why do you say that? Very good, exactly. They are telling us in the example that cosine is a negative function. So if cosine is negative, secant being its reciprocal function is also going to be negative. So there you go. We have our secant function. So based on secant, what can we find next? Yeah, cosine. So what do you think cosine of x is going to be? Negative 3 over square root of 10. Very good, because it's the reciprocal, but we cannot leave that square root of 10 on the bottom. So rationalize your denominator, which means multiply both the numerator and denominator by square root of 10. And what does that clean up into? Very good. So it will become, again, keep your negative sign, right? So -3 square root of 10 divided by 10. Alrighty, nice job. All right, so we've got cosine, secant, and cotangent. What do we want to do next? To find. Okay, so which one are you leaning towards? Okay, so you want to do the 1 plus, cosine square plus sine square identity. So let me see, how do I want to write this down? We're trying to find the sine function, so you can actually do sine square of x equals, what should that be if we're trying to isolate the sine square function from our Pythagorean identities? Yeah, very good. Move the cosine to the other side and you will get 1 minus cosine squared of x. Does that make sense? Okay, let me pull that one up again. So this is the identity we're looking at. This one right here. You're trying to get the sine square by itself, which means you start by subtracting that cosine of square to the other side, right? So that's kind of what we're doing here. And which gives you sine square equals 1 minus cosine square of x. All right, and then your cosine function we just found out is -3 square root of 10 over 10. And you still need to square that. What will that end up giving us? 2 negatives will of course become a positive. Okay, so 3 squared will become? Did you say 9/10? Okay, so negative times negative will become positive. 3 times 3 will become 9. The square root will cancel out the square, so you'll actually just have 10 on the top, and then 10 times 10 will become 100 on the bottom, right? If you take that square and put it on each value, but then 10 can go into 100 10 times. So yeah, you are going to end up with 1 minus 9/10. And what will be 1 minus? Okay. Why did you say -1/10? Oh, no. Just 1/10. Alrighty, so at this point we have sine squared of x equals 1/10. Yes? Any questions so far? Okay, now what do we do? Yeah, we still have to get sine by itself, so take a square root on both sides. So you will get sine of x equals positive or negative square root of 1/10, which will come out to be positive of -1 over square root of 10. And then to clean that up, very good. Very good. Now, what was our sign supposed to be for the sine function? Negative, yeah. Because again, remember, since cosine is negative, tangent is positive, that means sine also had to be negative. So that's going to be sine of x equals negative square root of 10 over 10. So you can see it's not just about coming up with the value of the function, right? We also have to be very careful about, is our value going to be a positive or a negative? Okay, so we found sine, we've got cosine, we've got cotangent, we've of course got tangent. So what are we missing now? Cosecant. Okay. So what is cosecant? Yeah, because if you actually go back to where we started out with, you can kind of look at this function right here, right? 1 over square root of 10. So if you just take its reciprocal, that's going to be square root of 10. Now, if you want to use the final answer that we got, which means you have to go back and rationalize the denominator one more time. So just to show you, if you did the reciprocal of 10 over square root of 10, which was just taking the value of the sine function and inverting it, you will need to rationalize your denominator for this. And then reduce by 10. So whichever part seems the easiest to you, you can also use the original definition you started out with. Use that. You can use this. I mean, options are up to you. So cosecant. Okay, and did we have secant? Yes, we did. That was, yeah. All right, so we've got tangent, which is given to us. We found cotangent here. We found secant, cosine, sine, and cosecant, right? All 6 functions, yes. Yes, you could have used the Pythagorean identity for that one also. So since we actually found cotangent right after tangent, right? You could have used that to find cosecant, and then from cosecant you could have gone down to sine. Yeah, I mean, just use whichever identity which you think is going to be nice to use or easy to use. You can definitely start with those. Yeah, and that's the beauty about these functions, is you're not restricted to just one method. You can use any of these which seem to make sense. Okay. Any other questions? Alrighty, so let's take a look at our second example here. This is actually now talking about simplifying a trig expression. So you were given sine of x times cosine squared of x minus sine of x, and you're basically trying to see how far you can simplify that. So you will notice here, we're actually using factoring to begin with, because both of these expressions separated by the minus sign have a sine x, sine x. So we're actually taking the sine x as our greatest common factor, and we're factoring it out, which means from the first expression, we are left with cosine squared. Since we took the sine of x outside, you're actually just left with 1 from there. And then they are actually trying to use the idea of the Pythagorean identity. So to put this in the right order, you will see we need the cosine function to be negative and 1 to be positive. So they're actually factoring out one more negative sign, or basically a negative 1. From that, if I take a negative 1 outside, this positive will become negative and the negative will become positive. By doing this little thing, I'm actually using my Pythagorean identity. So 1 minus cosine square of x will be sine square, and then you can multiply these guys to get a nice negative sine cubed of x. So we're actually going to be doing almost something similar with our example here. You're given cosine squared of x multiplied with cosecant of x minus cosecant of x. So let me go ahead and write that down. So cosine squared of x, cosecant of x minus cosecant of x. So what are you going to do here first? Yeah, very nice, because again, that cosecant is common to both parts of our terms. Go ahead and factor that out. So from the first expression, what are you left behind with? Yeah, very good. Cosine squared x minus, and then since this guy only had cosecant and we're taking that cosecant outside, you're going to put a placeholder. So that's going to be the number 1. So remember, this is your basic factoring. If I were to go back and multiply cosecant inside the parentheses, I should come back to my original expression. So that's why we need to put a 1 in there, because when I multiply cosecant of x times 1, it will go back and give me this term. Okay? All right, so you will notice we are actually in the same boat as our example 2 was. We need to switch that order of 1 and cosine square. So we will need to factor out a -1 again. So I'm actually going to take out a -1. That cosecant of x will stay the same, but now the signs inside the parentheses will change. So just to show you how the sign changes, cosine square was positive, so he becomes negative. 1 was negative, so he will actually become positive. So by taking just that -1 outside, I am actually able to switch the signs inside my parentheses. And then here, I can use my Pythagorean theorem. So again, remember your Pythagorean theorem is sine square of x plus cosine square of x equals 1. If I subtract both sides by cosine square, these guys cancel out, leaving us with sine square of x equals 1 minus cosine square of x, and this is actually the substitution that we're making. So since 1 minus cosine square of x equals sine square, I can make that substitution, I guess, happen here. That negative cosecant of x will stay the same on the outside. And then 1 minus cosine square has now become sine squared of x. Now, what do we know about the cosecant function? It's the reciprocal of the sine function. So I'm actually going to bring that idea in also and write it as 1 over sine of x multiplied by that sine square. And what do you think will happen when we simplify it? Cancel one of the sine functions out, right? So one of the sine functions will cancel out, leaving us behind with just a negative sine of x. And you know, some of them will take a little bit of practice to get used to how to simplify these. And that may be just kind of playing around with the different identities and seeing what helps out. Like here? Yeah, so what happens is I want this to look like 1 minus cosine square, not cosine square minus 1. So that means I need my 1 to be positive and I need my cosine to be negative. And I can do that by basically bringing out a negative sign. Because again, remember what I said, the idea is if you go back and reverse the process, you should go back to the original problem. So if I take this negative sign and I multiply it inside the parentheses, the negative with the 1 will become -1, right? Negative and negative will become positive. So that's why we're bringing the negative out. And then all I did was just rearrange the 1 and the cosine square. So it looked more like this. Like why I brought the negative out? Well, when you move the 1, that was a -1. Oh, okay. But yeah. It's still +1 because that's what we made it happen. Okay. So now it seems okay? All right, good. Did anybody else have a question on this? Okay. If you think of something, let me know. All right, so this was simplifying our function or our expression. Now let's look at factoring. So they're saying when trying to factor these trigonometric expressions, it is kind of helpful to find a polynomial form that fits the expression. So let's take a look at what exactly do they mean by that. Finding a polynomial form that fits the expression. So here we've got secant squared of theta minus 1. So you can actually think of 1 as being 1 to the 2nd power, and then I can use my difference of squares. So it's basically a squared minus b squared, which factors into a plus b, a minus b, or they're actually using the expression u squared minus b squared. So it doesn't matter because with difference of squares, when you factor something like this, it factors into u plus v, u minus v. So what we're actually doing is thinking of that 1 as 1 squared. So then you're doing secant of theta plus 1, secant of theta minus 1. And basically all they want us to do is factor these expressions. For the second one, now that's a little bit of an interesting problem. You've got 4 times tangent squared plus tangent theta minus 3. So this one actually is kind of using this trinomial form, because I've got the second degree on my leading term. I've got the first degree in my middle term, and of course 0 degree on my constant term because there's no tangent theta on the last one. So this is where they're basically looking at, okay, what would be the factors for 4 times negative 3, which would basically add up to give you positive 1, and then they're using that property to basically factor these guys out. So you've got 4 times tangent theta minus 3, tangent theta plus 3. And again, the idea is if you were to go back and FOIL this, you should come back to the original expression. So we're just actually using factoring a trinomial here to help us come up with what the factored form would look like. We've got exactly similar examples in our problems 3 here, A and B. So let's go ahead and try and factor those guys down, and let's see how we can do difference of squares and factoring a trinomial with trigonometric expressions here. So our first one is 1 minus cosine squared theta. So same thing like I showed you in example 3, sorry. You can write that 1 as 1 squared, because again, we know 1 is the only number you can put it to any exponent and you still get the answer 1. So 1 times 1 is still 1. And like I said, you're still using that difference of squares example where it factors into a plus b, a minus b. So if 1 is my a, cosine theta is my b, that's going to be 1 plus cosine theta and 1 minus cosine theta. So again, remember this is called difference of squares. All right, now let's think about how are we going to factor part B, which is 2 times cosecant squared theta minus 7 times cosecant theta plus 6. If it helps, instead of cosecant, put an x in there. So if you have 2x squared minus 7x plus 6, how would you factor it? Because it makes it easier if you don't have to keep thinking about cosecant, secant, or whatever those function values are in there. So think about how would we go about factoring this expression. You're saying 2x minus 6? Okay, so again, we just want to verify we're going to come back to the original expression. So I know when I multiply negative 6 with negative 1, I get positive 6. Okay, now for the first term, I know 2x times x also gives us 2x squared. So it's really that middle term we want to be sure about. So to check for the middle term, it's a very easy process. Multiply the 2 inner terms. That's negative 6x. Multiply the 2 outer terms, which will be what? Negative 2x. Adding them together gives us negative 3x. So what happened here? Where would you make a change? Are you talking about bringing the 2 outside? Yeah, bringing the 2. Okay, it still wouldn't change because even if you went back and did the FOIL, you're still going to come up with the same result. So the expression you're actually, one second, Sydney, the expression you will come up with no matter what order you do it in, you're still going to end up with that negative 8x in the middle. Okay, go ahead, Sydney. No? Okay. So we still know 2x times x is going to give us 2x squared. So that part I probably would not change. Probably still leave it as 2x and x, but I'd probably make a change on those last terms. Yeah, so let's try with 3 and 2. Because they also give us 6. Now again, what signs would we want both of them to have? They still need to be negative. Very good. So now, again, a quick check. Negative 3 times negative 2 still gives us positive 6. 2x times x still gives us 2x squared. So now, will we have that middle term? So these guys multiply to give us negative 3x. What did these guys multiply into? 2x minus 2. Negative 4x. And then when we add those two numbers or expressions, there you go, negative 7x, which is what we needed. So this guy did not work out, but 2x minus 3 and x minus 2 does indeed work out for us. So now how would you bring it from the x term to our expression? Very nice. Look at that. So that would be parentheses 2x instead of x cosecant theta minus 3, right? And then what will my second parentheses look like? Very good. Cosecant of theta minus 3. Any questions on this one?
We're not using like x's, you just gotta make sure that
Go back and put the original function. Yeah, so essentially what we did was make this guy into an x squared and make this guy into an x. And then when you write the final answer, instead of x, put the original function. Very nice. Anybody else? Okay. All righty, let's see our next type of example here. Okay, so this one here is actually talking about, if it helps, go ahead and rewrite your expressions using only one trigonometric function. And usually, if you can actually bring it down to either the sine or the cosine function, it makes our solving of the example a lot easier. Because look at this example here. You've got cosecant squared and cotangent, right? So we won't just be able to use, let's call this x, and now factor it, because they're two completely different functions. So this is kind of where they're talking about, you know, go ahead and rewrite it by using just one function, and if possible, try to make it one trigonometric function, or try to at least make it into either sine or a cosine function. So in this case, you will actually see we're converting this into a cotangent function. So cosecant squared, this is actually using the Pythagorean identity here. They're replacing that cosecant squared with 1 plus cotangent squared, and then you've got your minus cotangent of x minus 3. Go ahead and, of course, simplify that, which basically means the 1 gets added with negative 3, which is where this negative 2 is coming from. And then you've got your cotangent squared minus cotangent, and the constant has now become negative 2. And then this is basically x squared minus x minus 2, right? And then you can factor it out. So just by converting that into the same function, we're actually able to simplify it a lot better. And we've got something similar here where they're giving the secant squared of x plus 3 times tangent of x plus 1. So what's the relationship between secant and tangent? You can go back to that first page and look at your identities. The Pythagorean? Yeah, I would go ahead and use that one. So 1 plus tangent squared equals secant squared of u. So this guy is example 4. Okay, so we are given secant squared of x plus 3 times tangent of x plus 1, and we're using the Pythagorean identity. which is secant squared of x equals 1 plus tangent squared of x. So this is where you're going to be making the substitution. Keeping the middle term the same. And of course the constant term the same. Now how do we clean this up? What do you do? Yeah, so go ahead and combine. Very nice. So that will give you tangent squared of x plus 3 times tangent of x. And of course, 1 plus 1 becomes 2, right? Now that they are the same function, so you can think of this guy as being your x squared. Think of this guy being your x. You would have x squared plus 3x plus 2 as your expression. And what will these guys factor into? Okay, x plus 2x plus 1. So again, we know x times x gives us x squared. 2 times 1 gives us 2, and of course, they're all positive. And then when I add 2 plus 1, I get 3, right? So you know this is going to work. And again, you can always do the little inside and outside to make sure you're getting the middle term. So that can also work. All right, so now how do you translate this back into our original? Tangent x. Very good. Tangent x plus 2, tangent x plus 1. So keep in mind, this would not be possible till you made them the same function, right? Leaving it with the secant square and the tangent of x would not work. So using, again, the Pythagorean identity, we make the substitution, and then we're able to factor it down. Question on this one? Okay. So continuing that same idea of, simplifying our functions, we've got sine of t plus cotangent of t times cosine of t. So we're again using the identity of the cotangent function to rewrite it as cosine over sine. And then in this case, of course, you will see what happens is you end up multiplying cosine with cosine, which will give you cosine squared, and you've got sine of t. Now, do you know what's happening here on the second step? What did they do? How did this guy become from sine t to sine squared t? Okay, not sure? Okay. The two Adrians, Ezra, Sydney. They're actually finding a common denominator. So what they have done is, since this guy does not have a denominator, they have multiplied it by this denominator of sine t. So that's what's made it sine times sine, which is sine squared. Now you will see we have a common denominator, right? Instead of two separate functions. And then sine squared plus cosine squared is your trig identity, right? So again, look at that Pythagorean identity, sine squared plus cosine squared equals 1. So that's actually where this 1 is coming from. And then you end up with 1 over sine, which is the reciprocal function for cosecant. So basically, every step has involved some identity that they have used to try and simplify this function. And then, of course, the idea of using least common denominator in this example. So we will be doing pretty much a similar sort of example here with number 5. We are given cosecant of x minus cosine square of x multiplied with cotangent x. So where would you start with this guy? And this is actually, let me go back to our handout a second. This is actually where they were saying either if you can try and write it as one trig function, you can, or try to write it in terms of sine and cosine. And that's actually what they basically did here, was try to rewrite all of these functions in terms of sine and cosine. So that's what we're actually going to try and do, and see if we can write all of these in terms of sine and cosine. So how can I rewrite that cosecant of x? Yeah, sorry, 1 over sine. Yeah, so rewrite this guy as 1 over sine of x. We've already got cosine of x, so let's leave him as it is. What about cotangent? Yeah, that same quotient identity, right? So this guy will be cosine of x over sine of x. So cosine times cosine will give us cosine squared. Now, do we need to worry about finding a common denominator here? No, because our denominators are the same, so you can actually just write it as a common denominator, and that would be 1 minus cosine square. All right, so now think about this. What can you do here? Yeah, very good. Because again, you're actually back to that Pythagorean identity. So this is where, again, that sine square of x plus cosine square of x equals 1. If I subtract that cosine square of x, and this is the same thing we had done before, you get sine square equals 1 minus cosine square. And that's where the substitution will happen. So 1 minus cosine square will become sine square of x. You're dividing it by sine of x. What do you get? Sine x, yeah. The sign on the bottom is getting rid of one of the signs on the top. Giving the sign. No, I'll give you a printout of that because, you know, the idea is even if you switch one function, you get the whole thing wrong. And I'd rather you know how to use it than memorize it. So I'll definitely give you guys the printout. Oh, this guy here, because you're multiplying these, right? And that original cosine is basically, you can think of him, oh, come on, as being cosine over 1, right? So you're just multiplying the numerator with the numerator, cosine times cosine, right? Okay. Any other questions that are popping up in your mind? So like I said, these identities and the simplifying and factoring is definitely going to take a little bit of practice to get comfortable with them, because, you know, not every person is also going to do them in the same way. It just depends on what identity you remembered first and which one you ended up using. All right, let's take a look at these guys here. So now we're getting into adding our trigonometric functions. Our example here is sine of theta divided by 1 plus cosine theta. And you're adding that to the expression cosine theta over sine theta. Be careful about, again, these examples because each problem is going to be different. Some of them you may want to use an identity to try and make it into a different function. Because, you know, cosine theta over sine theta would be what? Cotangent, right? It would be the cotangent function. So there can be a lot of temptations to use the identity, but you have to see which approach works the best. So as you can see in this example here, we actually just used the idea of finding a common denominator. So the expression on the right-hand side, we're actually just multiplying it with 1 plus cosine theta on the numerator denominator. The expression on the left-hand side, we're multiplying it with sine of theta on top and bottom. So this is ending up being sine theta times sine theta. This is cosine theta times 1 plus cosine theta. So you're actually going ahead and multiplying these expressions and then cleaning it up from there. So you've got sine squared plus cosine squared plus just cosine of theta. Now sine squared plus cosine squared is our Pythagorean identity, which becomes 1. You're left with 1 plus cosine theta, which actually can cancel out with that denominator 1 plus cosine theta, leaving you behind with 1 over sine theta, which then becomes cosecant of theta. So a little bit of a different approach on how we go about combining these. So that's what I'm kind of saying, that every problem is going to take its own unique approach. If you did something in the previous example, that's not necessary. You can use it in the next example. All right, so let's go ahead and take a look at number 6 here. I think we should be able to get it done in the time we have. So you are given 1 over 1 plus sine theta, adding that with 1 over 1 minus sine theta. So do we want to find a common denominator? Alrighty, which means you are going to multiply the expression on the left-hand side with 1 minus sine theta. You're going to want to multiply the expression on the right-hand side with 1 plus sine theta. And that means for the denominator, you just end up multiplying the two original denominators. Okay, so 1 times anything is going to be the number itself, right? So you will end up with 1 minus sine theta plus 1 plus sine theta. Since you're only multiplying by 1, those values in the parentheses basically stay the same, and then you're just adding the two of them together. But what's going to happen on the denominator? This is, go ahead.
We use the, what is that one? Reverse the 1 plus and 1 minus.
Yeah,
Is that?
that's exactly what this is. Very good. Yeah, so you're actually reversing the difference of squares process, because now what you have is the a plus b, a minus b, because we have the same terms just with a plus and a minus sign. So when you FOIL this, your middle terms cancel out, leaving you with just the first term squared minus the second term squared. So we can apply that here. This guy will become 1 squared minus sine squared theta, which is of course just 1 minus sine squared theta. And then what happens on the numerator? And what happens with your sine function? Yeah, because you've got a negative sine function and a positive sine function. So that negative and positive sign is actually canceling itself out. And then you're left with 1 plus 1, which comes out to be 2. What can we do on the denominator? Yeah, because this is again the Pythagorean identity. So that will become your cosine squared theta, because again, you're using the property, your Pythagorean identity, which is sine squared theta plus cosine squared theta equals 1. So basically this time you are subtracting that sine squared theta. Can I simplify this further? Sure. We're right now at 2 over cosine squared. So If I take that 2 on the outside for now,
Oh, yeah.
what will that become? Yeah, inverse of 1 over cosine is basically your secant function. So lots of identities moving here and there, trying to see how we can combine these, how we can simplify them. All right, guys, so of course this is chapter 2. Chapter 2, we have 5 sections as you saw. It's going to be a while before we get to our chapter 2 exam.